Hello, Gordon.
Hi.
Yeah. The connection is smooth, right?
For me it is.
Yeah. Because my class earlier at noon did not go through. So it was
Huh.
weird. How many exams do you have, Gordon?
I have 3.
So are you taking only 3 classes or is it just that only
Just
three
just
exams?
3 finals. My other 2 classes I just had to write some reports.
Okay, let's begin in case we stuck with time, or maybe we should wait for Curtis too. I think he's always there.
Yeah, Dr. Shudders, I haven't gotten the evaluations back from everybody yet. I was going to come print them today. I sent another email, so hopefully
Okay.
it's not anybody that's here. So
Okay. What you could do is that go ahead and submit rest of them, and then you can send the other one using by email to the secretary, I think.
okay, yeah, I'll be there today after class. Then I'll run to campus.
Yeah, even Dr. Talapatra should be good enough if you can just send it to them. Yeah.
Okay, sounds good.
In fact, if you have all of them by email and you don't want to come just for this, you can send it to Dr. Talapatra. I think if it is all in one email, don't send too many emails to him. Yeah.
Oh yeah, that's okay. I can come bring the copies I have in person. I had to print a lot of small papers for the Elks anyways, so I was gonna come use my free prints at the school. So I'll be there anyway.
Okay. Thanks again. Yeah.
Yeah, no problem.
Okay, we have, oops, good luck. Okay, So we have the final exam, that's the only thing remaining. So, third Monday, G45. 4:45, that's the actual time, but it will be uploaded in the morning, uploaded in the morning. And due by evening. Evening is vague, but probably 11:59. So evening, so yeah, let's finish it off on that day, that's all. Any questions concerning the finals or anything? Okay, so we want to do what is called Cherenkov radiation. Okay. We built the formalism needed for this. We have a spectral spectral distribution of radiation, a formula for that. So if there is any, remember what radiates is anything that accelerates. If there is a charge that accelerates, that will radiate. So I should say any charge that is accelerating will radiate, or if there is any current which is changing in time, not just a current itself, a steady current will not radiate, but if it's a current that's changing in time, because current is equivalent to velocity, and if it is changing in time, velocity, rate of change of velocity is acceleration. So either changing current or accelerating charge will radiate, and that is how cell phone antennas and other things work. And we found a expression for the energy radiated per unit frequency per unit solid angle. Solid angle is look into a certain direction in space, and a small tiny angle, a cone of angle that you make out of it, that how much radiation goes into that cone, that's the solid angle. And how many, if there are lots of frequencies that it is emitting, which frequencies are emitted into that particular solid angle. And the expression for that we found is, there is a 1/4 pi. We kept that so that whenever you integrate the solid angle, it comes out to be total 4 pi. So that's a normalization for that. There is a constant which has the dimensions of resistance. It is the property of a vacuum itself, interestingly. And there is k squared over 2 pi. And we said it is the current that contributes to this. So instead of, it is a time derivative of the current density, but time derivative in frequency space becomes a frequency times current in the frequency space, right? So this k is the derivative, is the piece, like whenever we take a derivative in time space, in the frequency space, that's equivalent to having minus I omega, right? So it gets multiplied by omega. Here k is the vector k that we are going to be writing is omega over c in the direction of r hat, which is the direction of a solid angle in which you're measuring the solid angle. And the length of this vector will be just omega over c. So k squared has an omega square over c square. So it's a squared quantity, power has a squared, so each one will. So the square of the acceleration is what contributes to radiation. In time domain, it is the frequency times the current density, Fourier transform of that, complete Fourier transform, both the time and position, and then you square it. But then you also subtract out the charge density. This is just a way of writing it. So this is k omega squared. And that's so in that sense, it's very simple expression, no integrals or anything involved. if we know the current that is causing the radiation, Fourier transform the current, and you know exactly what kind of radiation it is going to emit. So kind of beautiful in that sense. So having defined this, let me write K is equal to omega over C times R hat. That's your expression, and we started working on, if with this expression, let's say we try to investigate what happens to a small charge that is moving with constant velocity. So that's a positive charge, charge Q, and it's moving with velocity V in the direction of Z hat, uniform velocity V. And I just now told that if it is not accelerating, it is not going to radiate. And that is correct. This will not radiate. So that will be our first result, that we will show that this does not radiate. But we are going to show that what is Cherenkov radiation is that, yes, this does not radiate if it is in vacuum. That's correct. But if it is in a medium, even though we always say that things cannot go faster than speed of light, that's not a completely correct statement in the following sense. In a medium, light gets slowed down, right? That's what the definition of refractive index is. Refractive index is the ratio of speed of light in a medium over speed of light in a vacuum. So light can go slower than speed of light. If there is another speed, that means a particle maybe can go faster than the speed of light in a medium. And in that case, it is still going with uniform velocity, but it might radiate. And we want to see what kind of radiation that is. That is what is called Cherenkov radiation. So you're going actually faster than speed of light in the medium, which is possible. And with uniform, even with you're going with uniform velocity, you'll have radiation in that case. And we started working on this. Let me redo those calculations. We want to calculate the rho of R prime in this case is simply charge Q times its position. It's on the Z axis, so X prime is equal to 0. Y prime is equal to 0. And its Z prime keeps evolving, right? As time goes, its position Z keeps changing and is decided by the velocity V. And we have chosen it to be at t equal to 0, at time t equal to 0, it is right at the origin. Right? So that's your charge density. Its current density, and let's say this is T prime, right? I said T prime. Its current density is simply Z velocity times Z hat. So that's your velocity because it's going in the Z hat direction, times everything else as we have charge density, just multiplied by charge. So it's pretty much identical. The current density will be the charge density itself multiplied by V times Z. So once you know charge density, we pretty much know current density also. So we want to calculate the Fourier transform of this quantity. So let's calculate the Fourier transform. This is K omega. So Fourier transform of this. So that's dx prime, dy prime, and dz prime, and dt prime, right? That's your 4 pieces for the Fourier transform. And exponential of I, this is I omega t prime, and minus I k dotted with x prime, k dotted with r prime, which is nothing but kx times x prime plus ky times y prime plus kz times z prime, right? That's what that stands for. And whatever the charge density is, so this is q times delta of x prime, y prime, and delta of z prime minus vt prime. Okay, so it's in the board space, I suppose. Yeah. So let's evaluate that. The three integrals, I can evaluate all the x, y, and z prime integrals there. So that's equal to all the three integrals gone. There is only p prime remaining. So there's a q that comes out. So that's minus infinity to plus infinity dt prime. And wherever I see x, y, and z, I have to put it 0. So x prime is 0. So this goes away. Y prime is 0. And the t prime stays. And this is minus I. Kz stays. Kz. And z prime is vt prime. But kz, remember, our vector k is equal to omega over c times r hat. Right? So kz would be k dotted with z hat. That's kz, which is equal to omega over c times r hat dotted with z hat. Is that visible? Yeah. R hat dotted with z hat, it's like this particle is going in the z direction, and we are actually making the observation somewhere in the r hat direction. And the angle between them with respect to z axis is in spherical coordinates angle theta, right? So it will be cosine theta here. So this will be omega c times cosine theta. So this quantity here, kz, is omega over c times cosine theta. Is that visible? Hopefully. Yeah. Okay. Let me rewrite this just once. So this is q times minus infinity to plus infinity dt prime exponential of it prime as an omega also as 1 minus v over c times cosine theta. Integral of an exponential is simply a delta function, right, which is clear in the sense we have used this before. If p prime was equal to, sorry, not p prime, the argument, so there is omega times 1 minus v over c. If this was equal to 0, then the exponential of 0 is 1. The remaining integral is infinite. But if it is not 0, it is oscillatory. So oscillatory integrals give you 0. In that sense, it is a delta function. So this is equal to q times 2 pi times a delta function of omega times 1 minus v over c times cosine theta. And we are again talking about a particle moving with uniform velocity, and you would say if this contributes to radiation, but it doesn't, because this delta function is always 0, because when does this contribute? Whenever v over c times cosine theta is equal to 1. When does that contribute? Whenever this becomes 1. When does this become 1? Cosine theta is less than 1, like less than or equal to 1, let's say. And v over c is less than 1. So unless you're going with speed of light, there is no chance it can radiate, and this is always, this is never going to radiate. So this is, which is not surprising, but we are going to get, we're going to make this contribute by the fact that if speed of light was slower than the speed of, in the medium, if the speed was slower than speed of light, then this will change a little. So we want to reformulate that. Before that, let's get one thing cleared. Let's go back to this expression here. And we are interested in the square of this quantity. So rho, so our expression for spectral radiation depends on the square. Right? This is square of this quantity that contributes. So there are two terms. So let me go back to this expression here. So that's q squared times minus infinity to plus infinity dt prime times exponential of, since it's a magnitude square, I had a complex conjugate it. So it's minus it prime omega 1 minus v over c cosine theta. And that is another piece, identical piece, which, since there are two integrals, I won't use the same letter. I will use t double prime, e raised to minus I t double prime omega 1 minus v cosine theta. Okay, so I'm just going to manipulate this equation a little before I start working on things going in a medium. So in that integral, let's substitute two new times. Let's substitute t prime plus t double prime over 2. That's an average time if you want. We will call it the macroscopic time. And let's call it tau as sorry, this should have been plus. Okay, so I should go back and point out I said it, but then I did not do it. I was going to complex conjugate it. So this is plus. So this is plus because this is a complex conjugate, and when it's complex conjugated, all the imaginary square root of minus 1 should be made plus, or change sign. So so tau will be defined as t prime minus t double prime. That's going to be the substitution. So we want to change our integrals accordingly. So I'm interested in the area integral of dt prime, or let's just say d tau, dt d tau, right? We're doing a two-dimensional integral involving these two as a differentials. This is given in terms of the Jacobian as the partial derivative with t prime, partial derivative of capital T with t double prime, and partial derivative of t or tau, actually, tau with t prime, and partial derivative of tau with t double prime. And this is called the Jacobian. It's basically the thing that connects the two area elements. When you make a transformation, what's the connection between dt prime, or dt prime and dt double prime, and this is given by this. And whatever you get using this determinant, you have to take a magnitude of that, so that's a double line. If you do this, we get 1 over 2, 1 over 2, 1 and minus 1 times dt prime, and that's simply 1, right? So this is exactly equal to dt prime and dt double prime. So that's a way to transform your integral. I expect you to have somewhere seen the Jacobian in some mathematics course. If not, let's say this is a quiz. Just look up what a Jacobian is, and this is where we are using it. So using that, we have our charge density in the Fourier space to be equal to q squared. Now we don't integrate over tau, we integrate over dt and d tau. Write that separately. This is dt and d tau. And the nice part of this is that the two pieces that can be combined as exponential of I, t prime minus t double prime is tau, and that's it. There is only one exponential piece there. So that's a simplification, and the whole thing is tau capital T independent, the macroscopic time independent. The T prime minus T double prime is the microscopic time if you want. And this can be taken into the energy on the left-hand side itself. And we have an expression now, which can be interpreted in the following way. You have the energy per unit time now, a macroscopic time, per unit frequency, per unit solid angle. So energy per unit time is kind of, this is T goes from minus infinity to plus infinity. It's like the power. So you say power per unit solid angle per unit of frequency. So that's equal to, go back to our earlier expression. So this is equal to mu naught over C 4 pi and 1 over 2 pi. Let me write this as omega square over C square. And that is Q square. And since J and current density and charge density are just different by V square, so this will be equal to V square minus C square. And we have a delta function, which is 2 pi times delta function of omega times 1 minus V over C times cosine theta. The same expression as earlier, we just rewrote it in terms of our macroscopic time. Let me process this a little. Let me cancel the 2 pi. Let me put the C inside. And remember that delta function of A times X is equal to delta of X over magnitude of A. So what we have here then is 1 over 4 pi not C over 4 pi square. I'll take the C square in. There is an omega that comes out. So let me write this as omega square over magnitude of omega. So since I don't, this will be a positive anyway. So actually I can write this as magnitude of omega. That comes after integrating this omega. Then there is Q square dependence. And when I put in the C, that's V square minus C square minus 1. And that is again this delta function, 1 minus V over C times cosine theta, which of course doesn't contribute where if you're moving with uniform velocity, which is a statement that uniformly moving charge does not radiate. But now let's go to a medium. How do we go to a medium? It's easy. We just have to change the speed of light, right? So wherever we see these quantities, we just have to change that. And we're going to say that, let's say, the whole region wherever we are investigating is filled with the same medium. So let's go back and see that if it is vacuum, we have the following idea that 1 over C square is epsilon naught times mu naught. If it's a uniform medium, then the speed of light changes. Usually we write V here, but I've already used the V for the particle that is moving. So I'll use C prime square. So C prime is the velocity or speed of light in the medium we are talking about. And this is not epsilon naught anymore. This is a property of the medium, epsilon. And typically that is frequency dependent. And similarly, mu naught is mu, which is again frequency dependent for a medium. Let's divide these two quantities. And when we divide this, we get, let me divide the first one divided by, no, I want to divide this over that. So what we have is C square over C prime square is equal to epsilon omega over epsilon naught times mu omega over mu naught. This can be written as speed of light c over c prime as square root of these quantities. Okay. What is c over c prime? The speed of light in vacuum over the speed of light in a medium. If you recognize this, this is actually the refractive index of a medium. So that's the definition of refractive index of a medium, n, right? When we do ray optics, we say that refractive index of glass is about 1.5, refractive index of water is 1.3. What that means is that speed of light in that particular medium is slower by a factor of 1.5. That's what it means. This can be written in terms of these two quantities. Let's write an epsilon to be equal to epsilon over epsilon naught, square root of that, and mu will be mu over mu naught with the frequency dependence. So what we have is n is equal to n epsilon times n mu naught. So how do we change our expression to a medium? So notice, if we were in a medium, all my speed c gets replaced by c prime now. But c prime itself is actually equal to c over n. So I start with my expression for vacuum and replace wherever I see a speed of light with speed of light over n, refractive index, and I have an expression for the same radiation in a medium, as far as this is a uniform medium filled with a sufficient region of space where radiation is happening and where it is being observed. There's also, we have to change that mu naught has to be replaced with mu, which is actually equal to, so the mu is actually equal to mu naught times n mu square. And same thing with epsilon naught, but epsilon naught doesn't show up in. So that's a simple prescription. We have to go from one medium to from speed vacuum to a medium. With that, we can now write our expression as, so our radiation per unit time, per unit frequency, per unit solid angle is equal to 1 over 4 pi. Let me write mu naught c over 4 pi itself. But then wherever I see a mu naught, I'll replace it with n mu square. And wherever I see a c, I'll replace it with a c over n, so that's over n. Where n itself, remember, is equal to n mu times n epsilon, if you want. But I can do that also, but let it stay as it is for clarification. So that's omega square over c square. Is this visible? Stop writing a little bit. Oh, I have to actually show the other expression. Okay, that's good. Okay, so that's omega square. Oh no, I'm going too far up. I want to do this omega. The magnitude of omega stays as it is. Q square stays as it is. V square over c square. So this becomes v square over c square, but c has to be replaced with c over n, so this is n square minus 1. And the same thing with the delta function. It's 1 minus n times v over c times cosine theta. That's it. That's your expression. Pretty easy actually. We just got it by prescription. And now let's see whether this radiates or not. Now the condition for radiation is no more that V over C, there is an added refractive index which is greater than 1. And the claim is that yes, this can actually radiate. And let's see what happens. So our condition for radiation becomes 1 minus n V over C times cosine theta has to be equal to 0, which means cosine theta is equal to C over V times 1 over n. So cosine theta will contribute whenever something is less than 1. And this is greater than 1, but this is also greater than 1. So there is a chance that if you're having, let's say, C over V is less than, or no, greater than, right? Is greater than 1 over n. Is that what the condition is? No, right? That's not what I meant to say. C over V has to be less than n. C over V has to be less than n, and then this will contribute. Both could be greater than 1, right? So this is of course greater than 1. But n has to be greater than the ratio of the speed of light versus the particle. So that means that the particle goes faster than, so the way to say it is that, what is it? Yeah, C over V, C over n, which is C prime, right, is the velocity is greater than the speed of light in vacuum. So then it contributes. And what kind of radiation is this? That's an interesting part. That this is a delta function in angle only when theta satisfies this. Remember, we had a particle that was moving with velocity v in the z hat direction, and only along an angle theta, which is governed by this ratio, only on this direction at a certain moment, as it is moving, this whole cone keeps moving, only on that cone will it radiate. Like for example, if you're standing here, you won't see it. If you're standing here, you won't see it. But this is a whole cone that is moving with the charge. So if you were standing here, you won't hear anything, and then suddenly you will hear something and it's gone. Right? That's like a shock wave. That's exactly how a shock wave goes. Or similarly, you see this in water also, right? A similar effect. If there is a boat going and there is a wake behind it, all the energy, most of the energy in that mechanical wave is in that wake, in that boundary of that cone that is forming that wake. And if you were in a very small boat right next to it, as the wake goes through, you get a tremendous amount of wave that is going through. So that's very similar here. As this goes, you see a shock wave. So this is called a shock wave. So that's one characteristic, that it's only for one small angle. The other thing is that this energy is proportional to frequency, right? So larger the frequency, more is the radiation. So out of all possible frequencies that it can emit into, it emits more into higher frequency. So in the visible region, you see a lot of, so there is more blue, so more blue than red, because blue has higher frequency. So whenever you see this radiation, typically what happens is that there are cosmic rays that can travel very fast, and you make a pretty much a detector which is a huge tank of water. And if there is such a radiation, it will see that, and this water turns blue. So this radiation is blue in color. That's a signature. So that's the two properties you can immediately calculate, and you can actually calculate how many photons are emitted per unit, so that there is more precise information there. But we won't go into that. That's a very small extension of that, but we won't go in there. I'll just say by look up the quiz, look up an image for, let's search for Cherenkov radiation and look for an image. Just look it up. You don't have to post it as a homework. Just look it up, and it's kind of a nice thing to observe. And that's all. I will not go beyond this. So I'll stop here. And thanks for listening, I would say.
Thank you.
Thank you.
Thank you.
Yeah. And we will have the exam on Monday.